Good morning, everyone. Welcome to today's lecture on biochemical engineering. So we will be discussing about aeration in detail today. And let's start in a couple of minutes. For your friends to join, we will wait. Okay, so let's quickly recap what we have seen yesterday. So we were talking about aeration and what are the types of spargers available to induce aeration, then factors affecting the cellular oxygen demand, and then we have seen what is specific oxygen uptake rate, OUR बोलते हैं उसे. Now I told we will be talking about oxygen transfer from gas bubble to a cell. That is, you have your sparger which has sent you a bubble of oxygen. ठीक है, तो अब यहाँ से from that gas bubble, how is it oxygen molecule going to get into the cell for itself to breathe? So it has to breathe, right? That's why we are giving oxygen. So what happens is there is a layers of transport that is happening for the gas bubble to reach its target. सबसे पहले वो यहाँ पे जो अंदर है, नंबर वन इज इनसाइड द गैस बबल, वहाँ से वो गैस लिक्विड इंटरफेस में आएगा. दिस इज द गैस लिक्विड इंटरफेस. Interface is the place where your gas bubble meets with the liquid media, जो आपका मीडियम है जिसमें आपने माइक्रो ऑर्गेनिज्म को ग्रो करके रखा है वो. तो वो यहाँ से जो ये इंटरफेस को पार करेगा, दैट इज नंबर 2. एंड नंबर 3 जो है वो लिक्विड फिल्म है. दैट इज अ थिन लेयर ऑफ लिक्विड विच सराउंड्स द गैस बबल. इमीडिएट कॉन्टैक्ट में जो है उसे लिक्विड फिल्म बोलेंगे. बाकी तो पूरा लिक्विड ही है, बट इमीडिएट कॉन्टैक्ट में जो लिक्विड है वो लिक्विड फिल्म होगा. Okay, that's why they have put it in a dotted line. It's imaginary. There is no hard and fast layer such thing. Okay, it's imaginary. तो यहाँ पे number 3, that is number 3. So number 1 inside the cell, number 2 is at the gas liquid interface, number 3 is in the liquid film. The movement happens through the liquid film, then it moves outside into the bulk. Okay, so यहाँ पे जो है पूरा number 4 दिया गया है. That is the movement of oxygen molecule in the bulk liquid. अब वो दो जगह जा सकता है, या तो वो इंडिविजुअल सेल या फिर सेल क्लम्प, मतलब क्लस्टर ऑफ सेल्स, मोर नंबर ऑफ सेल्स अग्रीगेटेड टू ईच अदर, वहाँ जा सकता है. इफ यू सी वो यहाँ अगर इंडिविजुअल सेल में डायरेक्टली जा रहा है तो 5, 6 and 7 7 जो है उसकी जरूरत नहीं है. 5, 6, 8 जो है वो डायरेक्टली यहाँ पे वापस एक गैस सॉलिड लिक्विड इंटरफेस होगा एंड लिक्विड फिल्म वो क्रॉस करके अंदर इंडिविजुअल सेल में आ जाएगा. ओके, इंडिविजुअल सेल है तो ज़्यादा प्रॉब्लम नहीं है, बट ये केस ऐसे होता नहीं है बिकॉज माइक्रो ऑर्गेनिजम्स दे आर लिविंग इन कॉलोनीज, राइट? दे डोंट लिव एज इंडिविजुअल सेल्स. तो यहाँ जब सेल क्लम्प में आता है क्या होगा? फर्स्ट it has to get into the liquid film again. Okay, and from that liquid film it has to cross this solid liquid interface. Solid, why? Because the cell is a solid, and liquid because on the other side of the cell is the liquid media. So solid liquid interface, and from the solid liquid interface it moves into the cluster of cell clump. यहाँ पे चला जाएगा पूरा. Then it goes inside to an individual cell here, and that is a place where site of oxygen reaction takes place. That is a place where oxygen is used up. Okay, ये है इसका mechanism. So to understand this, I'll show you a video, and then after that video, we will see the video on the role of spargers also. Okay, so first this mechanism which I just explained, we will watch that. You can see the video screen.
Let's get started.
Shown is a simple schematic of modern protein therapeutic production processes. Our focus today is optimizing cell culture. Many factors impact this, and one of those is aeration. One of the most important functions within a bioreactor is the delivery of oxygen to cells through a process called aeration. This is normally done through sparging of air followed by mixing. This is the cell respiration reaction.
Okay, so this is why we need oxygen for the cell to respire, okay, for it to breathe. So what happens when oxygen combines with glucose? Glucose is the food. It gives carbon dioxide, it gives water, and it takes up the energy. जो cell को energy चाहिए वो, ठीक है? अब carbon dioxide released out, water is also released, or it is in the body plasma, okay? And this is what they are saying: 15,000 to 16,000 times more soluble than oxygen. Which one? Glucose is, okay? And oxygen dissolves at 7 milligram per ml rate, okay?
For this reaction to occur, both glucose and oxygen need to be dissolved in the media so that they can be utilized by the cells. While glucose solubility is high, oxygen solubility is exceptionally low, and therefore needs to be supplied continuously and controlled carefully during operation. Here we show the cell growth and protein production reaction. Oxygen and glucose are also necessary for biomass expansion and protein production. Since oxygen is the rate-limiting reagent in terms of solubility, it is important to optimize the delivery of oxygen to the cells. The rate at which oxygen is transferred to the media is known as the oxygen transfer rate, or OTR, which remains effectively constant for a set of bioreactor conditions. The rate at which
So what they are saying, they have already made it very clear that oxygen solubility in the liquid medium is less when compared to the glucose solubility. So transfer rate is higher when compared to the oxygen uptake rate. Uptake by the cell is lower, or sometimes if you are giving constant oxygen, then they may be equal. Otherwise, oxygen transfer rate is higher than or greater than the oxygen uptake rate.
The cells in the culture utilize and uptake oxygen is known as the oxygen uptake rate, or OUR. Initially, the OUR will be low but will increase as the cell density increases. The OUR will increase until the OTR becomes the limiting factor. Thus, the rate at which oxygen is transferred to the media defines the theoretical maximum cell density. Bioprocess engineers define the rate of oxygen dissolution in terms of a parameter known as KLA, or volumetric mass transfer rate. KLA defines how much oxygen is available to cells for growth. This parameter is necessary for cell culture optimization and scale-up. OTR is determined by KLA and the dissolved oxygen, or DO, concentration in the media. KLA, in turn, can be manipulated through process and operational parameters. These will be discussed in Part 2.
Thank you for listening. And for more information on
Okay, now this is another video in which we will talk about the impact of sparging. Why is sparging necessary and what is the impact of it? Okay, so now we know that oxygen is important, and since the oxygen solubility is less, you have to give constant supply of oxygen. Okay, and how it is achieved, that is by sparging. We will watch this video now.
welcome to another 2 Minutes Tuesday technical training. Let's get started.
This schematic shows how most protein therapeutics are produced and purified using mammalian cell culture. Our focus today is optimizing cell culture. Many factors impact this, and one of these is sparging. For the purposes of bioreactor cell culture, sparging is the introduction of air, and more importantly, oxygen, to the cell culture media. Once the oxygen is dissolved in the media, it is used rapidly by the cells and therefore must be fed continuously via specially designed spargers. However, oxygen is sparingly soluble in culture medium, thus how the sparging of oxygen is conducted becomes very critical. Low oxygen solubility and its rapid uptake by cells means that dissolved oxygen concentration can limit cell growth. The amount of dissolved oxygen is impacted by two major factors: interfacial area and residence time. Smaller bubbles have a larger surface area to volume ratio, or interfacial area, than large bubbles. Increasing the interfacial area allows oxygen to dissolve more easily and quickly into the culture media. The transfer of oxygen from the bubbles to the cell culture media also requires adequate time for the oxygen to dissolve and transfer from the bubble to the media. Small bubbles created by the sparger rise more slowly through the bioreactor, which translates to longer residence times. The design and location of the sparger relative to the impeller location are critical design considerations for adequate distribution of bubbles in the bioreactor. Typical sparger designs can be grouped into two major categories: macro and micro. Open pipe and ring spargers generate larger bubbles compared to sintered spargers. The table shows the characteristics of the various types of spargers, but generally speaking, sintered spargers are used for single-use or small-scale operations where cleaning is not a major concern. For large-scale production, ring and open pipe spargers are more commonly used.
Thank you for listening. And for more information on
Okay, so now we have seen how sparging is done, And what is the impact of sparging? So they say the smaller the size of the bubble, greater the interfacial area, and you can work more on the solubility factor as well. Okay, so now moving ahead with what we were talking. Okay, so we were looking at this mechanism. Now there is two places where there is an interfacial transport. First is at this gas liquid interface, and second is at the solid liquid interface. At both the places, the mass transfer coefficient plays a very important role, and that's why we need to determine the KLA value. Now, what are the 8 steps for oxygen transfer from from a gas bubble to the cell? The first one, transfer from the interior of bubble to the gas liquid interface. Second one, movement across the gas liquid interface. Third one, diffusion through relatively stagnant film surrounding the bubble. Fourth, transport through the bulk liquid. Fifth, diffusion through the relatively stagnant film surrounding the cells. Sixth, movement across a liquid interface or the solid liquid interface. Seventh, if the cells are in a flock, clump diffusion through the solid to the individual cell. Then eighth, transport through the cytoplasm to the site of the reaction. Okay, inside the cell. Eighth one is inside the cell. Now, when I'm talking about an individual cell where there is no clumps, that time seventh step is not applicable because it is directly from the solid liquid interface, it is directly moving into the cytoplasm. Okay, now note, resistance due to the gas boundary layer on the inside of the bubble has been neglected. If the cells are individually suspended, step 7 disappears. Okay, so that's what I was telling you. Now, we have seen this particular image in that video also. Oxygen transfer rate is greater than or equal to oxygen uptake rate, and at steady state where there is no accumulation of oxygen in the liquid phase. And how can we determine KLA value? So there are different situations. The first is at steady state where there is no accumulation of oxygen in the liquid phase. Okay, that is in the bulk. So the rate of oxygen transfer, OTR, must be equal. At steady state, it must be equal to the rate of oxygen uptake, that is OUR, by the growing cells. Okay, what they are saying is there is no accumulation in the liquid phase. That means there is no loss. So whatever oxygen is given by you, introduced by you inside the liquid medium, should reach or should be uptook by the cells. So the rate at which the oxygen is transferred should be equal to the rate of the oxygen that is uptaken by the cell. So, and this is the value of this is the general equation wherein we get KLA. Okay, so since KLA is equal to concentration of the dissolved oxygen minus the concentration, I mean saturated dissolved oxygen concentration minus the normal dissolved oxygen concentration is equal to Q naught X. Now what is Q naught and X? Remember we have studied Q naught earlier. Do you remember it? X is the cell concentration. What is Q naught? I'll show you here where we have studied it for you to recollect. See, so what is small Q naught? It is the specific oxygen uptake rate, right? It is given here, this part. So Q naught is a specific oxygen uptake rate. So this equation KLA into C star AL minus CAL is equal to Q naught X. With this, you're going to tell how you can determine the KLA value. Okay. So for a given set of operation, for a given set of operating conditions, the maximum rate of oxygen transfer occurs when the driving force is also maximum. X max is equal to KLA into C star AL divided by Q when C is equal to 0. So when C is 0, this equation you get. X max is the maximum cell concentration. Rate of oxygen transfer from the bubble to the liquid phase by the equation dCl by dt is equal to KLA into C star minus CL. We are talking about the rate of oxygen transfer from the bubble to the liquid phase, where KL is a volumetric mass transfer coefficient, and A, where it here A, KLA, right? And A is the gas liquid interface area per liquid volume. Okay, so if the O2 concentration, that is Cl, O2 concentration is Cl, cell concentration is X. Remember the terms if you want to understand it. So if O2 concentration, that is Cl, is the limiting factor in cell growth, then QO2 is a strong function of dissolved oxygen concentration. Cl is equal to, that is given in terms of milligrams of O2 per liter. The relationship between QO2 and Cl is of the monad type. Okay, so with what is QO2? What they are saying is it is like Ks. How you have in monad equation, you have mu is equal to mu max S by Ks plus S, right? How, what is the role of Ks? It is a limiting substrate concentration. So if your oxygen is the limiting factor, that is, if you give too much of oxygen, if it will die, or if you give too less, also it will die. If oxygen plays as a limiting factor, then this QO2 is having a direct impact on the Cl as well. Okay, so that's what they're saying here. If you remember, this is how the monad graph was also drawn. Here you have the QO2 values, and here you have the oxygen concentration Cl. So if at initially what happens when the oxygen concentration increases, the QO2, that is a limiting factor, the growth with respect to the oxygen is also increasing. After a certain stage, it is going into a stagnancy. Okay. Now, when O2 concentration is a limiting factor or limiting substrate, then, so just like your mu is equal to mu max S by Ks plus S, you will correlate with that, you will remember this equation easily. So QO2 is equal to QO2 max Cl divided by KO2 plus Cl. Okay, mu इज इक्वल टू म्यू मैक्स एस बाय के एस प्लस एस, वैसे वाला इक्वेशन है, तो इन दोनों लगभग सेम हो जाता है. ओके, सो यहाँ पे हम जानते हैं क्या है, के एस क्या है एंड एस क्या है, एंड ऑल वी नो दैट. ओके, सो नाउ this is the equation which we have derived so far. Ki what is KL, what is KLA, then CL, then Q क्या होता है, ये सब हमने देख रहा. अभी जो है हम आगे जो देखेंगे वो है डिटर्मिनेशन ऑफ KLA वैल्यूज. आप KLA वैल्यूज को कौन से टेक्निक से डिटरमाइन कर सकते हैं. देयर आर 3-4 टेक्निक्स. द फर्स्ट वन इज अ सल्फेट ऑक्सीडेशन टेक्निक. नेक्स्ट इज योर गैसिंग आउट टेक्निक. एंड गैसिंग आउट में दो है, एक है स्टैटिक मेथड एंड दूसरा है डायनामिक मेथड. एंड देन we will be talking about the key variables of that affect the KLA values. तो ये जो है हम methods of determination of KLA value हम कल देखेंगे. अभी के लिए आपको ये वाला मैकेनिज्म याद रखना है जिसमें 8 स्टेप होते हैं. What are the 8 steps? First one, movement of gas bubble from movement of gas from inside to the interface. Then movement of the gas from through the interface, not from, through the interface or across the interface. And then movement of the gas from the interface to the liquid film or through the liquid film. And then movement or transport across the bulk. Then movement in the liquid film, and then movement across or transport across the solid liquid interface, and then transport across the bulk to reach the individual cell, and then from the cell into the cell cytoplasm where there is a site of respiration. Okay, 8 steps ये आपको याद रखना होगा. Then and then you have this oxygen transfer rate greater than oxygen uptake rate, and then these are all the equations that we have seen. Okay, so just if you have any doubts you can let me know, otherwise I'll take the attendance now. अभी तक मैंने क्वेश्चन फॉर चैप्टर 3 नहीं डाला है. बिफोर यू आस्क आई विल टेल. Vaibhav, I'll check and tell you. मैंने check नहीं किया होगा. When did you mail me, Vaibhav? नहीं, मुझे आपका असाइनमेंट नहीं आया है. Okay, so you can resend your assignment. I have not received it. Okay, so answer your attendance. Viber present. After giving attendance, you may exit the meeting. Yes, Mukesh, आपका आ गया है. Mohit Kacha, roll number 1, 2, 3,
Yes, ma'am.
2, 3, 4,
Yes, ma'am.
5,
Yes.
6,
Yes, ma'am.
7, 9, 10, 11, 12, 13,
Yes, ma'am.
14, 15, 16,
Yes,
17,
ma'am.
okay,
Yes,
17,
ma'am. Yes,
18.
ma'am.
Yes, Paras, I have marked you present. 19,
Present, ma'am.
20, 22,
Yes, ma'am.
24,
Yes, ma'am.
25, 26, 27,
Yes, ma'am.
28,
Yes, ma'am.
29,
Present, ma'am.
31, 32,
Yes, ma'am.
okay, 33, 34,
Yes, ma'am.
okay, 36,
Yes, ma'am.
37, 38, 40, 41, 42. Giriraj, please wait. I'll finish the attendance and I'll get back to you, okay? 42, 43, 45, 46, 47, 46. जब मैं नाम कॉल आउट करती हूँ तब अटेंडेंस नहीं दोगे, बाद में मैसेज आएगा मैम मेरा एब्सेंट हुआ है. 47, रुतुल, प्रियांक, पार्थ,
Yes, ma'am.
okay, विवेक,
Yes, ma'am.
ऋत्विक, एंड तर्पण, उत्तम,
Yes.
ओके, चंद्रेश, ओके. उत्तम आप प्रेजेंट हो? ओके, यहाँ पे रह गया था, अब मैंने कर दिया. C star Al is a saturated dissolved oxygen concentration, Giriraj. That is the, we can tell if the bubble is too much bigger and it is too difficult for it to dissolve. So it is in saturated state. It is too much in concentration. Okay? That is saturated dissolved oxygen concentration. Okay, Vivek, you are present. Any more doubts?